Recording. Today, chapter 9, relational programming, finally. And we're going to make some parallels with Karuta. So, let's first start by establishing what is a relation. So, this paragraph does it all. A
You
procedure
were
in a
not
declarative...
sharing the screen yet.
Oh, sorry. There you go.
Thank you.
A procedure in a declarative model uses its input arguments to calculate the values of its output arguments. This is a functional calculation in the mathematical sense. The outputs are functions of the inputs. For a given set of input argument values, there is only one set of argument values. The one set of output argument values. We can generalize this to become relational. So a relational procedure is more flexible in two ways. First, there can be any number of results to a call, either 0, 1, or more. Okay, so first of all, we need to put a slight question mark, no, not question mark, a slight asterisk on this sentence. Because you may say, oh, you can actually return multiple values in a functional way as well. You can just put
Yeah,
them in
that
a tuple.
yeah, that's not what this means.
Exactly. But putting them in a tuple is already unifying them to a single output value. This means that you're not grouping the results together to make them a function in a mathematical sense. And you're going to see how that works in a bit. And second, which arguments are inputs and which ones are outputs can be different for each call of such function. Which is also very powerful. We're going to talk a little bit more about that. So this is very well suited for databases and parsers. I actually have no idea how this is useful for parsers, but we're going to
We're
see in
gonna see
9.4.
that.
We're going to see
We're gonna
9.4.
see that, yeah, in the next session.
I do know how that's useful for databases. I'm not going to go into this tangent, but I'm going to say that I do understand it.
Also, Warren mentioned.
Yeah, this is the same warring of
Yeah.
the Warring's abstract machine, right? That was kind of like, okay, that's very cool. Anyway, so for a programmer's point of view, relational programming extends declarative programming with a new kind of statement called a choice. We already seen this before in Karuta. Conceptually, the choice statement non-deterministically picks one among a set of alternatives. During execution, the choice is implemented with search, which enumerates the possible answers. We call this don't-know non-determinism, although the search algorithm is almost always deterministic. And this is a very old idea, apparently. So we are like late to the party or something.
Standing on the shoulders of giants.
Standing on the shoulders of giants, exactly. And then we have watch out for efficiency. And why is that's the case? Because it's commonly understood that when you're doing relational programming, you're doing a brute force algorithm, which means that you are exhaustively checking all of such alternatives. So that is a challenge to make it efficient. So it can easily lead to highly inefficient programs. This cannot be avoided in general since each new choice operation multiplies the size of the search space by the number of alternatives. So this becomes exponential. The search
Yeah.
space is the set of candidate solutions to a problem. But relational programming is sometimes practical when the search space is small. It is saying that this is typically the case for database. I don't quite believe it, because if you
Well,
have a table in a
data.
database with like
Oh,
a petabyte of entries,
well, databases, they tend to be careful to um, ensure that every query terminates, right? That's not true in general for relational languages.
yes, but my statement still stands. This is very hard to believe that this is the search space is small in a production environment. Another example is the diagnostic generator. I can buy that and as an exploratory tool. So we can use it for small examples, even though it's impractical for bigger examples. So the advantage is that the programs can be much shorter and easier to write. No algorithm has to be divided, since search is a brute force technique that avoids the need for algorithms. This is an example of non-algorithmic programming. So this is like we are going full-blown naive mode. We're gonna brute force this shit.
Basically, yeah.
Um, so we're going to talk about that. And apparently there is ways to optimize the shit out of this, which is actually pretty annoying because it's chapter 12, which is very far away from chapter 9. But apparently this is called constraint solving, constraint programming. And this may apparently is an evolution of relational programming, which I'm very excited to see how that works. So now talking about the relational computation model. Um, so we're going to introduce choice and fail to the model, to the declarative model. The choice statement groups together a set of alternative statements. Executing a choice statement provisionally picks one of these alternatives. If the alternative is found to be wrong later on, then we backtrack, hence another one is picked. The fail statement indicates that the current alternative is wrong. So this is another way to, like, instead of you just depend on the unification failing, you can also explicitly say fail.
Yeah,
Yeah, this is being said in here. Fail is executed implicitly when trying to bind two incompatible values, such as 3 equals 4. And then we have a Magetta example.
yeah. I
So,
immediately thought of him when I saw this for the first
yes,
time.
exactly. That was the same with me. So what is this? We're trying to make all the possible combinations for clothing. So we have a function called soft, which has two possible choices, beige and coral. And we have hard, which has two possible choices. I don't know how to pronounce this, and neither this one.
Mauve and ochre.
And then you have a procedure called contrast that picks two um, let's say, variables, and you make a choice by binding C1 to the color soft and C2 to the color of hard, and you do another choice doing the opposite, and then you make a function calling contrast 2 times for shirt, pants, and socks. Um, and you check if the shirts is going to be equal to socks because this is like a business thing, so you can fail. Otherwise, you just construct your suit. Pretty cool.
Very nice.
That creates all the possible suits, arrangements of suits available, given this combination. So you have to think that this is creating alternatives, and these are also creating alternatives, um, which creates a search tree that looks like this, right? So you're going to explore, and this is well, not necessarily the case, but this can be depth first. This could be breadth first. This could be another strategy. Which,
Yeah,
by the way, would be very nice. I don't know if I'm saying bullshit right now, but I feel like that it would be nice to be able to dynamically change the search.
yeah. The Oz idea allows you to do that because it has a notion of encapsulated search.
Which gives me the perfect context to ask, are we going to do that in Karuta?
It would be nice actually because
Okay, before we go into that, let's explain what it is. So what is an encapsulated search? Right? So this is essentially, I like to think about it as a closure. So you have each choice. Um, um, so let's put it like this: you want to run which one of these subtrees in a separate thread, but you know that in order for them to proceed, they need to do binds. They need to do assumptions to keep proceeding on the search. If you don't protect each subtree from each other, that would be very hellish, right? Because one thread would be interfering with the bind of another thread, and everything will go to hell. In order to solve that problem, you essentially make each search of each thread in a copy of that tree that they are sharing, so that they don't interact with each other. That gives you the ability to run them concurrently. And then you just have to make a strategy to combine them later, which I'm assuming if you're trying to mimic Prolog semantics, you're going to go depth first, priority system or something. So if after all the threads are done, you're going to rearrange them in following what would be done in a sequential depth first search. And that gives you the ability to run them concurrently. Now you can continue saying what you were about to say.
um Yeah, encapsulated search it does two things, right? It allows you to, first of all, avoid unpleasant interactions between threads, right? It basically allows you to do a nested query, right? And the second thing is, in this case in particular, we're not going to see this here because the relational model is based on Prolog, but when we get to the constraint model, which has the full-blown, you have everything in it, that allows you to actually choose the search strategy. So it basically allows you to parameterize how you iterate through the choices
But for
at
each
each point.
thread?
For
Oh,
each
for each
encapsulated search,
alternative of the choice.
yeah, like
Okay.
basically, we're gonna see later on, like it's kind of crazy because chapter 12 shows you how to implement chapter 9, but basically it's going to show you, okay, given that we're using encapsulated search fully now, here's how you can control the search strategy. Um,
Yeah. Um, okay. Is my explanation of encapsulated search fair?
it is.
Okay, I have a question. This sounds expensive as fuck.
Is it?
Yes, because you are essentially duplicating the the subtrees. You're copying them.
You actually don't have to do that, but even if you do that, if you use persistent data structures, you can avoid a lot of copying. I guess it depends on how you go about it. One possible strategy is to just avoid actually binding the variables until you are sure that your search is going to succeed. Like do the binding at the end and have a kind of local environment where you say, okay, I'm going to bind this, but I'm not going to commit yet because I haven't finished my search. So I'm going to do the lookups here first, and only if I don't find it here, I will then block on the variable.
But even if you don't bind it, Marinho, my understanding is that the environment for each thread in the beginning, everybody will have a copy of the same thing, and as they move along, they will be doing the binds for each particular alternative that it's necessary or not. They can do what you said, which is to avoid the bind and like postpone it after you are sure that it's going to succeed. But at the end of the day, in the beginning of the race, you're going to have to copy whatever is the starting point for each one of them.
Not necessarily,
How not?
actually. Um, how not?
When I
Uh,
say environment, I mean the stores. Okay? I mean like the trigger store, the store that does immutability, the single assignment store. All of
the
those will have. My understanding is that we're gonna have to copy all of those for each one. That's my understanding.
No, the trick here is that there are only a few well-defined points where you have to be careful about interacting with the environment. Specifically, you have to care about any um, any unbound variables, and in particular, variables that are introduced by the search itself as well, right? They have to be isolated.
Yeah, what you said is very much aligned with what I said. But you said that
Mm,
what I said is not necessarily the case. I want to understand why.
Because you can do essentially copy on write. That's the naive one naive way to do it, where you say, okay, I need to bind this, but actually I don't want to bind it yet, so I'll make a local copy of it, and then later, when I succeed, I'll grab all of my local copies and actually bind them to the actual variables. That's
Oh,
one
so
option.
it's basically like copying by demand. On
Yeah,
writes,
you
I mean.
yeah you can do that on demand. That's one option. The other option is it depends on how your runtime system is implemented to begin with, but like in Carta, we have an actual map of bindings, right? And that map is a persistent data structure.
Yeah.
When you're using a persistent data structure like that, you don't have to copy anything at all. You can just alias the data structure, and it's immutable, right?
Well, then back to the question. You have the map of bindings. One thread wants to bind A to one, and another thread wants to bind A to two.
The
How are we
the
gonna
maps
how are we gonna handle this situation?
Well, in our case, the maps are immutable, right? So it's perfectly fine for one thread to say, okay, in my local reference to the environment, I'm going to make a new version with this binding. Um,
So you are
but
copying.
that no, you aren't. When you do a map update in Clojure or Erlang, for instance, when you have a persistent map, you don't have to copy the entire structure. You only have to copy a small part of it when you do an update.
Ah. Okay, now I understand. So you are exploiting the fact that you have persistent data structures, so you can only append the. You don't have to copy the entirety of the thing. You can only save the delta, I guess, the things that you were about to change from that point onwards.
Yeah, basically, this technique is called path copying because
Why this
persistent data.
book didn't mention that when they mentioned persistent data structures? Come on. Okay, go
Well,
on.
well, the Okazaki book is actually a really good resource for this kind of stuff. But basically, path copying means you're implementing your persistent data structure as a tree, and then when you make a change, you only have to copy the path from the root down to the leaf that you
Makes
are
perfect sense.
modifying,
Makes
and
perfect
everything
sense.
else can share the original structure because it's
Okay, now I
immutable.
understand what you meant by not necessarily copying. Copying would be a naive approach to this implementation, but you can do what you just said, which is more efficient.
Again, it depends, right? If you're implementing your bindings as a persistent map, you can do this. If you're implementing them with actual individual mutable cells that you are careful to let the runtime bind only once, then you have to do some kind of on-demand lazy copy on write, as I mentioned earlier. And if you're doing something else, I'm sorry, but you're probably crazy.
Yeah, but could you repeat the approach before what you just said, which is if it's mutable, you need to do the lazy by demand copy on write, right?
Yeah, because if you're taking the low-level approach where you say, okay, I don't have an environment map, instead I'm going to allocate each data flow variable or logic variable in this case as a small cell on the heap that I'm going to assign exactly once.
Mm-hmm.
If you're doing that, then you don't have a persistent map that you can manipulate, right? Which means
Mm-hmm.
you have to keep track of, okay, in this search, I'm binding this variable, so I'm making a local dictionary saying, if I try to read this variable, I'm going to use this local binding, and then
Mm-hmm.
only at the end, after you have collected all the bindings on a successful branch, you say, okay, this branch succeeded, so
I see. I see. So you're essentially like for this bind specifically, instead of doing a lookup in the global official store of variables, I'm gonna use my local copy that has already been changed for my particular subtree.
yeah, and then you only actually write to the outer scope
After
when
you
you
know it's gonna succeed.
after you know you have succeeded and picked an alternative, right? Because there may be multiple possible
Yes,
alternatives.
you also need to prioritize that. Hey, I succeeded. I also succeeded. Who is the one that's gonna actually apply the bindings, right? We need a strategy for that as well.
Yeah, the nice thing about this particular way of doing things is that it's potentially recursive, right? You can have nested search, and then
Mm-hmm.
each level writes to the level above, and then you have a top level where you're doing the where your program is running, and you only commit to that after you go succeed at every stage and reach the end of the search.
Yeah. Okay, encapsulated search is important for modularity and compositionality. With encapsulated search, there can be more than one relational program running concurrently. Since each is encapsulated, they do not interfere with each other. Um, well, except that they are using the same computer. They can be used in a program that communicates with the external world without interfering with that communication. Yeah. For compositionality, an encapsulated search can run inside a non-encapsulated search. So again, that's why I did the parallel with closures, because that also is true for closures, right?
Yeah.
Yeah. So essentially, this is cool. I thought this would be expensive, but Marinho proved me wrong, as almost always. You can definitely make this more efficient implementation. And again, I wonder if we're gonna do this in Carta. Like, what forbids us from doing that?
In some sense, we kind of already have that because mini microkernel is kind of it's monadic, right? So it's kind of encapsulated by default. The issue is that it's not parameterized. It doesn't parameterize the search strategy. We have to do that as a separate
No, but
step.
it's not parallel. The minikite
It's not.
implementation uses either a fold or a recursive function.
It's not
So,
parallel, but you can actually run a nested search if you have a primitive to merge streams, which I got bored on Saturday, so I started a sketch of that. Um,
oh, so you were doing Karuta on Saturday. Great. I actually like the first time I read this, I was like, okay, let's say that Marinho's gonna say that we're gonna do this. Can't we use the message passing from Erlang in the Minikari implementation to make this happen?
uh, Theoretically, we could, but that may not be efficient, is the problem.
Okay, but how would you? Everything is immutable in the Erlang side, so how would you make that efficient in this case?
The problem, the thing that it makes not efficient is that when you go through a message boundary, right? When you send a message to another process, you lose any ability to do structural sharing because you are not like you're moving through the wire, right? The structure is now flat.
Yes.
That's why I said it's inefficient. Ideally, you should be able to define a single-threaded version of encapsulated search to avoid that.
But
Um,
that's what we already have, right?
we kind of have that, yeah. We just need to be able to merge streams, and there's a very straightforward way to do that, and you're kind of golden already.
Wait, but then I have my then I want to know that's a single threaded version. How are we gonna make it concurrent? That's my question.
Um, well, we
I
can
thought of using
run.
processes to make it concurrent.
Well, in that case, yes. Basically, we should be able to spawn another Karuta process from Karuta at some point. Because we're on the bean, right? What are you doing if you're not doing that?
Yeah, but we have to be careful, right? Because we already know that every time we're doing message passing, we're doing copying. And that may be very
Yeah,
expensive, depending on what the fuck you're copying.
exactly. We have to be careful about that.
Um, anyway, so I think this is a pretty interesting point. And again, if we want to keep the prologue semantics, which I believe we do, this is just a matter of rearranging after like, okay, 50 paths succeed. Rearrange them in the order that would be done by a prologue like semantics in a sequential fashion. Then we already have the same outcome, but we did it concurrently. There's also a question of like, is it really worth doing concurrently? Because if you have 50 paths and you're gonna only pick one, didn't you waste resources computing the 49 other ones?
Uh, that's a problem for committed choice, which is a whole nother topic. Um, but it's not necessarily a problem in general if you're going to actually allow the other results to be potentially used later, right?
Yes. Yes. Yeah, but in our case, well, I'm not a professional logic programmer, but my understanding is that that's usually not the case. After you pick one single path that succeeded, you're gonna keep going on that path because if you, aside from like if you have deep down a failure there, right? Maybe if
Um,
you continue going, then okay, we succeeded in this 50, but after you, there's another search there, that there's another ones, and everybody failed, so I have to backtrack. Then we can reuse the 49 ones that we computed before. But then there's a question: how do you know for the lifetime of those results?
well, that's usually a problem that's left to the garbage collector. But um, in general, you only have to worry about not being able to backtrack if you have side effects. Because, like, if you send a message to launch some missiles, you can't undo that, right?
Yeah, but my understanding is that we're gonna go the prologue. Well, Mageta wanted to go the Mercury way, I believe, of actually having semantics for side effects, not like prologue that is just like impure.
Yeah,
Um,
the Mercury way is that basically anything that touches I/O has to be either deterministic or it has to do committed choice, which is if there is any non-determinism, you pick the first one that succeeds and discard all the others. So yeah, we have to do what you said if you want to go that route.
Yeah. Okay, and then the solve function. This is how Oz manages to mix the two very different paradigms of programming. So you have the declarative model that allowed us to do functional programming, OOP programming, declarative concurrency, shared stateful concurrency, all of those things. How are we keeping all of those things and adding the logic programming? This is how they did it. So actually, the logic program lives inside of a particular world that solve function is the way to get there. So this is encapsulated search by adding one function solve to the computation model. The call solvef is given a zero argument function or a procedure that returns a solution, one argument procedure, returns a solution to our relational program. So you're not actually embedded, like you're not in the environment that everything is relational. You choose to go relational. You choose to go relational. And then another important thing is that this returns a lazy list, right? So you have a function, a lambda here, that you are passing to solve as an argument, and there's a choice of three numbers, and this will return you the lazy list. The reason it's lazy is because this search may be very non-exhaustive, right? Because
Maybe
solve is lazy,
potentially, yeah, it may have potentially infinitely many results, right? If it's
it's
recursive.
not going to halt. It only calculates the solutions that are needed. Solve is compositional, and it can be nested. The function f can contain calls to solve. Using solve as a base operation, we can define both one solutions and all solution search. To get one solution search, we use solve one, which essentially calls solve, and then it demands the first one, the head of the list of the results. If you want them all, to get all solution search, we use solve all. That does a very interestingly weird thing, which is there is this touch function that in the first glance does absolutely nothing, right? So it just calls itself using the tail as argument, and this essentially, I spent 5 minutes looking at this, asking myself, what the fuck is this doing? Because we are not using the outcome of touch all, we're just returning the L. This touch all function is to unlazify the elements of the list.
Yeah, this is basically just forcing all the elements.
Yeah, you're forcing all the elements. And then we have computation spaces. So we introduced that, and now we need to introduce what is a computation space. Computation spaces are part of constraint-based programming computation model, which we don't know yet because it's chapter 12. They are originally designed for constraint programming, a powerful generalization of relational programming. So essentially, like, we're not going to tell you. This is for the future.
Yeah, we have to see that later.
Solving the clothing design example. So this is we're going to use the solve helper function to actually get all the outcomes, all the possible, all of them. And then we have further examples. So this is attempting to teach us how to program in this mentality. And differently than OOP and everything that we've seen so far, I think this is required in the book because it's a very different way of thinking about programming. You cannot just like say, okay, this is the same thing, but a little bit massaged to a particular trade-off, like OOP was. These we have to go from the basics. So we have the digit function, which essentially is a choice among digits from 0 to 9. And if you just solve them all, you're going to get a list of 0 to 9. If you have a two-digit function that is using the digit function twice, that has these choices, then you're going to get, and you apply solve all to that, you're going to see this outcome. And you may ask yourself, how is this possible? Well, you need to, preferably in your head, but if you feel that's hard, use a piece of paper, you need to draw this tree for this particular expression. And then you're going to understand. Well, it also depends on the semantics, on what is chosen to be executed first. But very naively, you're going to see that the result should be this, using all the possible choices.
Yeah, if you're doing that first, you're going to get disorder because the evaluation is of operations is left to right, right?
Yeah, and if you swap, it's the same expression, but you swap the things, you're going to get a very different outcome. And this is because of what Marin just said. It's depth first, so it matters the order of the who is coming first or second.
Yeah, in the declarative semantics, like you don't really care about the order of the results, but operationally you do. So that's why there's a difference.
Yeah. Well, you may say that semantically in this case is also different because this is not a set, this is a list. And in a list, the order matters. So this is also semantically
Um,
different in this case.
well, it needs to be a list because this can be potentially infinite, right? So this is not actually a list, it's actually a stream,
Yes,
technically.
that's fair to say. That's fair to say. But actually, I have a question. Why is this? I actually didn't. I understood the principle because well, I already seen this with my own eyes in Karuta. This difference, like if you swap the order of the clauses and stuff like that. But I don't know why 10 is the second member in here because this is gonna start by being. Yeah, this will go from 0 to 9 and this will stick at 0 in the beginning, right?
Yeah, this is because of how operations are desugared, right? In Oz, if you have an operation with two expressions, that desugars to binding the left-hand side to a temporary variable, then binding the right-hand side to a temporary variable and doing the operation on the temporaries, right? But this implies that the right-hand side comes after, which means we hit it first when we backtrack.
Wait. So we're saying that we're executing this digit first, then this one.
No, no, no. We're executing the one on the left first. But because of
Sure.
that, when we backtrack, we hit the one on the right first because it's the one that executed last.
But
Like
then,
this is
but stop there. Correct me if I'm wrong, okay? Because I must be wrong. These will not go from 0 to 9 and these will keep at 0. This will not happen.
no, it won't.
Okay. Because if it did, the outcome would be this, right?
Yes.
Okay, so what is this doing? What this is going to execute digits only for 0 and then these will go from 0 to 9?
Um, well, this will go from 0 to 9, and then when it exhausts all the possibilities on the right-hand side, then it's going to try the next one on the first expression and go to 1. You see?
Yeah, okay, so it is doing um,
It's depth first, so whatever you do last will be the first thing that you
yeah,
change when you do
yeah,
a retry.
exactly. The last thing is this. So this is going to be executed first. So it's like last in, first out.
Yeah,
This,
it's basically a stack, which is why Prolog is depth first, by the way, because you can use the call stack kinda. You can do just a bunch of nested stacks to do backtracking, and it doesn't use a lot of memory, right?
I
Compared to
see,
doing breadth first, where you have to
I see,
keep a huge queue of all the possibilities that you are still investigating.
I see. Palindrome product problem, very classic as well. And okay, so here's the tip. If there's anybody watching this and you don't are not understanding what the fuck is going on, my tip is instead of trying to write a series of transformations in a functional way, or if you want to like in an imperative way, because at the end of the day, imperative also implements a series of transformations. Instead of thinking like that, you need to think of what must be true in order for your problem to be solved. So if you think of a palindrome, um, these uh, equals here, these asserts, they all must be true if we actually encounter a positive case of palindrome. So that's
Yep.
the way to think about it. You need to think about it what must hold in order for the thing to be found. So all of these are properties of this particular problem. And then, well, you and I we understand this, so this is very fine, right? Nothing
Yep.
too crazy. And then we have puzzles and queen's problem. Yeah, this one is a little bit more crazy because this is the n queen's problem. You want to find all the positions that we can have in each particular column of a chessboard, having a queen in such a way that they will not kill it. They will not be threatening each other. And there are multiple possible solutions to multiple ways that you can organize the board with one queen per column that will hold. and the program is this program. I don't want to spend a lot of time on this program, but it's essentially the same thing about um, well, it is still stuff that must hold, but there's also like some normal quote unquote normal programming bits, such as having a function and a procedure. But you're essentially just calling those, and then these binds here are actually the statements. Well, the asserts. Let's call it like
Yeah,
that.
basically.
Yeah. So you need to again use a piece of paper. That's fine. And these are essentially the heights, right? The assuming each particular column from left to right, these are the heights for each queen.
Yeah.
And yeah, and if you do solve all, you're gonna actually see all of the solutions. Cool, 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 very cool. So now relation to logic programming, because so far, remember, there is a question hanging, the elephant in the room. What the fuck is the difference between a relational and logic programming? And this is actually answered at the end of this chapter, at the end of 9.3, so I'm very happy about that. So there's a brief introduction of logic programming. I think this is worthwhile to read. A logic program is a statement of logic that is given an operational semantics. It can be executed on a computer. If the operational semantics is well designed, then the execution has true properties. It is correct in the sense that it respects the logical semantics, which means that all consequences of the execution are valid logical consequences of the program considered as a set of logical axioms. And it is efficient. It allows to write programs that execute with the expected time and space complexity. Then we have propositional logic as like pretty much a foundation for the logic system you're going to use. Yeah, because that's the question. What is an appropriate logic in which to write logic programs? There are many different logics. So the foundation is going to be propositional logic. And then we have operators. Like this is all things we have seen. I'm not gonna say at school, but I'm gonna say like beginning of engineering courses or engineering degrees. Yeah, so you have and, you have or, you have if and only if, you have implies, you have not, you have atoms, which are essentially like indivisible
I find
parts
it
of a logical formula. Yes.
I find it very tragic that you cannot categorically state that you would have seen this in school.
Yeah, you definitely. It's definitely tragic, but it's definitely not true that people have seen this in school. Um, yeah, don't confuse this with an atom in a programming language. Like from this point onwards, you are like a blank sheet of paper. Okay, so everything is new. All the terminology is new. And then you have propositional logic allows to express many laws, such as the counterpositive. You also have De Morgan's law, which again, very basic for engineering courses and degrees. To assign a truth value to a propositional formula, we have to assign a truth value to each of its atoms. That creates a truth table. And if you have a formula that is true for all possible assignments of its atoms, this is called a tautology, which are the cases for the previous examples. And then we go to first order predicate calculus, which is essentially what Magetta, well, I think Magetta loves this thing, which extends propositional logic with quantifiers. Well, and a few more other things, right? Because you can also have variables and terms.
Yeah, it basically adds data structures and quantifiers is the main difference.
Yeah, so this allows you to,
You can
like
have
this,
tuples basically.
yeah, this allows you to have the concept of a free variable. Atoms in predicate calculus are more general than propositional atoms since they can have arguments. Here, x is a variable symbol, p is a predicate symbol, f is a term label, and li are term features. We have the quantifiers for all and exists, which are called quantifiers. In like manner as for program statements, we can define the free identifier occurrences in the logic formula. So if you have something like this, x and y are free, but if you do something like this, now they are bound. And in logical semantics of predicate calculus. Yeah, this is also very important. To assign a truth value to a sentence of the predicate calculus, we have to do a bit of more work than for the propositional calculus. Okay, so we have to go further than a truth table. We have to define a model. The word model here means a logical model, which is not the same as a computation model. A logical model consists of two parts: a domain of discourse, all possible values of the verb. So this is also the same semantics that we use for, like, when you're talking to product people in your when you're doing programming. You talk to them in a way the reason they can understand you is, if they can, is because you're talking in the domain of discourse, that they care. So so you give names to you put values to the variables, right? You make instances of the variables, and a set of relations, where a relation is a set of tuples. So these are essentially instantiations of the variables, and these are instantiations of groups of variables. Each predicate has a relation, which gives the tuples for which the predicate is true. Among all predicates, equality is particularly important. The equality relation will almost always be part of the model. The quantifiers for all when there exists range over the domain of discourse. Of course, usually the logical model is chosen so that a special set of sentences called axioms are all true. Such a model is called a logical semantics of the axioms. There can be many models for which the axioms are true. So the model is essentially an example that makes the set of axioms true. So let's see how this works with an example. Consider the following two axioms. So this is the classic familiar, relationships in a family example.
Genealogy, basically.
Yeah, there are many possible models of these axioms. Again, because models here, in the logical model, is an instance of the axioms that make the axioms hold. Here's one possible model. So the domain of discourse is going to be these, the father relation. These are examples that hold with the father axiom. We have the grandfather relation, which again is using the grandfather axiom, and you have the equality relation, which says that you are yourself.
Yep.
Identity, essentially.
Identity.
And the relations contain only the three tuples. All other tuples are assumed to be false. Okay, so
yeah, closed world assumption, basically.
With this model, you can give truth values to sentences of predicate calculus. For example, the sentence this, which is essentially saying that you are father of your father, can be
That you are
evaluated as being false.
Actually, this is saying you are your own father, which can only be true in some silly time travel stories, basically.
Yes, yes. Yeah, I think your version is better than my version because it's even more ludicrous. You are your own father. Note that the equality relation is part of this model, even though the axioms might not mention it explicitly. Okay, now how this relates to logic programming? Easy. Now we can state more precisely what a logic program is. A logic program consists for a set of axioms in the first order predicate calculus, a sentence called the query, and a theorem prover. A system that can perform deduction using the axioms is an attempt to prove or disprove the query. So essentially, like, you have a sentence, so like this one, and you want to see if that holds. And the set of axioms is actually the asserts that you write in a logic program.
Yeah, that's basically your code, right?
And the ability to do deductions on the axioms to verify the truthfulness of the query, that's the theorem prover, and that's the engine that you write when you write a logic programming language.
Yeah, it's basically your Prolog implementation or the
Exactly.
Karuta implementation.
Performing deductions is called executing the logic program. Can we build a practical programming system based on the idea of executing logic programs? There are three issues that we need to address, which are very cool. Theoretically, a theorem prover is limited in what it can do. It is all only guaranteed to find a proof or disproof for queries that are true in all models, right? So because again, models are examples, are instantiations of the axioms. So we can only prove or disprove queries that are true for all possible models. So for example, if I make another instance or like this one for this, uh, I can only prove or disprove things that are true or false for all of them, which is a limitation, right? Because maybe you only care about a particular model. You don't care about any of the other ones.
Yeah.
If you're only interested in some particular models, then there might not exist a proof or disproof, even though the query is true. We say that the theorem prover is incomplete. For example, we might be interested in number theory, so we use the model of integers with integer arithmetic. There is a famous result in mathematics called um, Gödel's incompleteness
Godels.
theorem. Gödel's incompleteness theorem. I always don't know how to pronounce his name. Gödel's incompleteness theorem, from which it follows that there exist statements of number theory that cannot be proved or disproved within any finite set of axioms. Yeah, we're not gonna go open this tangent, but this is a very strong result. Um, okay. Even in those cases where the theorem proving could theoretically find a result, it might be too inefficient. The search for a proof might take exponential time. A theorem proven intended for practical programming should have a single and predictable operational semantics so that the program can define algorithms and reason about their complexity. And then finally, they changed this, by the way, this paragraph.
Oh, they did.
Now it also mentions Gödel's completeness theorem.
I see. So it mentions both now.
Yeah. A final point is that the deduction done by the theorem proven should be constructive. That is, if the query states that there can exist an X that satisfies some property, then the system should be able to exemplify or construct a witness to the existence. It should build a data structure as an output of the logic program. So two approaches are taken to overcome these problems. We place restrictions on the form of axioms so that an efficient construct theorem proven is possible. The prologue language is based on horn clauses, which are axioms of the form. For all this, this, and this, and then we just put a bunch of disjunctions, right?
For all this, and this,
Where x1 to xk are chosen so that the axiom has no free variables. Horn clauses are interesting because there is an efficient constructive theorem prover for them using an inference rule called resolution. Which again, well, not again, right? This is also explained in engineering degrees, math degrees, or if you are a weirdo and you are doing, I don't know, history, but you do logic in the math department, they will probably teach you this. Um, the relational computation model of this chapter also does logic programming, but without using resolution. It uses a different set of axioms and theorem proven, which are discussed in the next section. We give the programmer the possibility of helping the theorem proven with operational knowledge. This operational knowledge is essential for writing efficient logic programs. For example, consider a logic program to sort a list of integers. A naive program might consist of axioms defining a permutation of a list and a query that states that there exists a permutation whose elements are in ascending order. Such a program would be short but inefficient. So this is essentially like, I want a miracle, help me please.
basically, yeah.
Much more efficient would be to write axioms that express the properties of an efficient sorting algorithm, such as merge sort, which is true, but um, pretty much puts the burden, a little bit of a burden of knowledge into the programmer. You need to know this already beforehand.
Yep.
You cannot just ask for a miracle naively. A major achievement is that we actually have practical logic programming systems such as Prolog, and they are efficient high performance Prolog implementations. And now operational and logic semantics. I'm also going to read this because it's worthwhile. There are two ways to look at a logic program: the logical view and an operational view. In the logical view, you are in one of the most high-level programming languages available. Because that means that the program is essentially a bunch of axioms, which is a statement of logic. In the operational view, it's an execution on a computer. So for example, we have the declarative model in chapter 2, where we see that programs in the declarative model have a logical semantics as well as in operational semantics. We already saw the operational semantics.
We did, yes.
It is straightforward to translate a declarative program into a logical sentence. And the reason is because it is deterministic and it is and because of the logic variables binding semantics. Um, if the program terminates correctly, which means it does not block, then all the bindings it does are correct deductions from the axioms. That is, the results of all the predicates are valid tuples in the predicates relations. We call this the deterministic logic programming. And then we have a translation table that translates any statement S in a relational kernel language into a logical formula, which is this table here.
This
So
is a
this
very
is
nice table.
there's a lot of things here happening here, but essentially what you need to understand in this chapter is, well, this section, is that the declarative model is already can be understood as a logic program. Because procedure
Yep.
definitions are translated into predicate definitions. Note that the exceptions are not translated because, of course, this raising an exception only like fails for the backtracking. The logical sentence therefore does not hold in that case. Proving the correctness of this table is beyond the scope, of course. And then there's a very funny phenomenon. A given logical semantics can correspond to many operational semantics. For example, we have these three pieces of code. All of them have the exactly same logical semantics, even though they have different operational semantics. So
Yeah.
this is a mapping of like many to one, in a sense. The first statement binds x and y and then executes s. The second statement executes s and then binds the variables. The third statement waits until it can determine whether x or not x or y are equal. And then it then executes if it determines that they are equal. So writing a logic program consists of two parts: writing the logic semantics and then choosing an operational semantics for it. The art of logic programming consists in balancing two conflicting tensions. The logical semantics should be simple and operational semantics should be efficient. Which, well, this is always the conflicting tensions of any higher level language. All the declarative programs of chapter 3 and 4 can be seen in this slide. They are all logic programs, including the declarative concurrency ones.
Yep, including those.
In the Prolog language, this has given rise to a beautiful programming style. And then there's like 3 references. Just go check yourself. Deterministic append. So now we're going to see an example of something that you usually would do with a functional approach, in a sense that you're using a function, versus using in a relational way. So we've seen this append before. So let's expand it to a procedure. You're going to have this thing, right? With a procedure, you're going to have an output argument. Because here we're just tail calling yourself.
Yeah, here the output is implicit, right? This makes it visible, basically.
This, following the translation table, we have these logical semantics for it. This procedure also has an operational semantics given by the semantics of the declarative model. The call executes successfully and returns x equals to the appended version of the first list and the second list. The call's logical meaning is the tuple append, which looks very similar. But the reason it's in italic, and I think this is a very important thing to clarify. This is not like programming. It just looks like it. But the reason it's written in italic is to make sure that you understand that this is just like a high level description.
This is a logical expression. This is basically a fragment of some predicate calculus.
Exactly. So this is
Statement.
not, because this is the clear separation, a very good example of a clear separation between specification and implementation. This is a specification in this case. We don't know how that's going to be implemented at all, but we know that it's going to be. This is what specifies the solution to our problem. So it looks different, and that's the reason it's written in a different way in italic. As Marinho said, you should understand this as a predicate calculus thing. But now we will see how to actually implement this specification. Well, we're gonna see this in a bit. So the above definition of append doesn't always give a solution, right? For example, this call would not do what must be done. Should return x equals to 1 shoe because 1 shoe appended with 3 gives the list 1 shoe 3. Remember, relational programming allows you to swap on each call which things are inputs and which things are outputs.
You can run things backwards, kinda.
Exactly, but the program cannot give this solution because of how it's written. So this program blocks. This shows that the operation semantics is incomplete. To give a solution, we need to write a version of append with a different operational semantics. To calculate x from the last two arguments, we can choose the definition of append as follows. And this is specifically tailored to this case now.
Yup.
Which, not surprisingly, gives the same logical semantics of the previous one. Well, not the same, but equivalent, right?
Right, because you can just do some, you can just apply some identities and recover the other one.
Exactly. And then we have the non-deterministic append. We have two versions of append with the same logical semantics but different operational. Both versions return exactly one solution. But what if you want this version? There are 4 different solutions that satisfy the logical semantics, right? Because you can have 1 shoe and then 3. You can have 1 and 2, 3. You can have 1, 2, 3 and empty, empty, 1, 2, 3. The declarative model is deterministic, so it can only give one solution at most. To give several solutions, we must use the choice statement to guess the right information and continue. And then we're gonna fall into using this version of the append. So the operational semantics that we chose before is not able to realize these logical semantics for all patterns of inputs and outputs. In the declarative model, the operational semantics is deterministic and directional. With relational programming, we can write programs with a more flexible operational semantics that can give solutions when the declarative programming would block. And this is called non-deterministic logic programming. So then we have this is the logical meaning of the append. And then the question is, how can we write a program that respects these logical semantics and is able to provide multiple solutions for this call? Look closely at the logical semantics. There is a disjunction with the first alternative and a second alternative. And every time, okay, so this is basically a tip. If you see a disjunction in what I said before was wrong. That was conjunction, the one pointing downwards. Well, with the pointing up, but with the other things down. This is disjunction.
And this is a norm, basically.
Every time you see a disjunction, you're going to use the choice. So this translates now into this.
Yeah, choice is basically logical war, essentially.
Yeah, we can search for all solutions to call this using the solve all. This gives us this series of tuples. So this is the value of x, and this is the value of y, and these are all the possible values of x and y. That solves this particular problem, question, right? This should be viewed as a question, a query. And then this program can also handle the directional cases. So if you swap for that, and then the program can even handle where no arguments are known at all. Since in that case there are infinite of solutions, we do not use solve all, but solve only. And then we have to touch each one individually. And then this displays the successful solutions, right? All possible solutions are given in order of increasing length of the first argument. This can seem somewhat miraculous. It certainly seems so to the first logic programmers in the late 60s and early 70s. Yet, it's just a consequence of the choice. But be warned that this type of programming, while it can sometimes perform miracles, is extremely dangerous. It's very easy to get into infinite loops or exponential searches to generate candidate solutions almost indefinitely without ever finding a good one. This is a problem in theory, but it's not a problem in practice, because if you're using relational programming what it's good for, the available space of solutions is limited. So if you're doing a database, for example, even if you have a petabyte of data to search, it's still known. It's a petabyte of data. It may take a while to search all of that, but at least it's finite. The other example of the circuits, I also believe, was the same thing. It was probably big, but finite.
Yeah, you have to be careful about recursive predicates when you're doing this.
We advise you to write down deterministic programs whenever possible to use non-determinism only in those cases when it is indispensable. Before running the program, verify that the solution you want is one of the enumerated solutions. Okay, and then finally, okay, we are almost done. The answer to the huge question: what the fuck is the difference between relational programming and logic programming? So, the relational computation model provides a form of non-deterministic logic programming that is very close to what Prolog provides. To be precise, it is a subset of Prolog called pure Prolog. The full Prolog language extends pure Prolog with operations that lack a logical semantics. I think they have printing, right? And I think printing lacks logical semantics.
And they have side effects. Like the side effects in general don't have a logical semantics.
Only in general. In Karate, they will, because going to the database is an effect, but they have logical semantics.
Well, yes, that's one particular case where, yeah, there is actually a logical semantics to that. So you can pretend that it's pure because it can give you a. There is a way to make a pure interface for it, essentially, right?
Yeah. But they are useful programming and that are useful for programming a desired operational semantics, such as printing, right? I'm not criticizing Prolog for having printing, particularly because printings are useful. Programs written in either pure Prolog or the relational computation model can be translated in a straightforward way to the other. And there are three principal differences between pure Prolog and the relational computation model. So the first of all is the operational semantics. Prolog uses horn clause syntax with an operational semantics based on resolution. The relational computation model uses a functional syntax because, again, you can go back and forth between the logic world and the normal stateful or declarative world with an operational semantics tailored to that syntax. But this is more of a difference between these relational programming implementation and Prolog.
Yeah.
The relational computation model allows full high-order programming. This has no counterpart in first-order predicate calculus, but it is useful for structuring programs. High-order programming is not supported at all in pure Prolog and is only partially in full Prolog. Okay, now I have a question. Would it be correct to say that logic programming does not support high-order predicates and relational programming does? And that's the one difference between them?
Uh, well, it depends on which logic system you are using as your foundation, right? If you're using like higher order predicate calculus, then yeah, you have higher order programming, but also your logic is undecidable. So you kind of, yeah, usually most practical logic programming systems are based on just the first order predicate calculus.
Because then they are decidable, right?
Because then the logic, the declarative semantics is decidable in that case, yeah.
Yeah, it makes perfect sense. It's less expressive, right? But it makes sense. The relational computation model distinguishes between deterministic operations, which do not use choice, and non-deterministic operations, which use choice. In pure Prolog, both have the same syntax. Deterministic operations efficiently perform functional calculations. It is known which arguments are the inputs and which are the outputs. Non-deterministic operations perform relational calculations. It is not known which arguments are inputs and outputs, and indeed the same relation can be used in different ways. But again, this is more of a detail of this particular relational computation model rather than
Um,
an abstract difference between relational and logical.
yeah, like you can have like Mercury allows you to have functions. So you it's not like uh, the relational model forces you, or rather, it's not like you're kind of stuck with one or the other, right? It's this is more of a detail. The main point is whether or not there is logical semantics to your program, right? That's the main. I think that's the most important point.
Yeah, but so far, the only difference I can see between relational programming and logic programming is the high order predicates.
Well, this is not talking about. Oh, keep in mind, this is not talking about relational programming in general. This is talking about specifically this relational computation model of the book, right?
Ah. No, but it talks in an abstract way. The relational computation model. It doesn't say the implementation of the relational computation model. Like,
Well, yeah, this is not talking about relational programming. This is talking specifically about the computation model that we are introducing in this chapter.
oh, okay, so I got too much excited for no reason. Because I still am asking myself, what the fuck is the difference between relational and logic?
I mean, you can do logic programming with functional languages if you're just using the deterministic subset of logic programming, right?
Yeah, but the deterministic subset is kind of like I don't see that as relational because you
That's kind of
are
the point. It is logic, but it's not relational because you don't have proper relations, right? You can't run your functions backwards.
yeah. So that's why I'm saying it's kind of misleading to say it's like deterministic relational programming. Like to me that's kind of like self-defeating in a way. But well, anyway, logic programming and other models. So now the question is, do we must use a declarative model to have logic semantics? And the answer is no. To have a logical semantics means that execution corresponds to deduction. Execution can be seen as performing inference, and the results of procedure calls give valid tuples in a simple logical model, such as a model of the predicate calculus. The basic principle is to enrich the control. We extend the operational semantics which allow to calculate new tuples in the same logical model. So let's go. Adding concurrency to the declarative model gives the model of chapter 5? No, 4?
I think it's four, yeah.
These models also do logic programming since they only change the order in which the valid tuples are calculated. They do not change the content of the tuples. Very fair. The non-deterministic concurrent model, which was briefly touched in chapter 5, does logic programming. It just adds one operation, which true, which can be given in a logical semantics, which is going to look, if you have a way true that looks like this, it's gonna look like this logically. Operationally, way2 waits until one of its arguments is determined. Way2 is used to manage control in a concurrent program, namely to pick an execution path that does not block. The non-deterministic concurrent model is interesting because it combines true properties. It has a straightforward logical semantics and is almost as expressive as the stateful model. For example, it allows building a client-server program with two independent clients in one server, which is not possible in a declarative model. We've seen this before. This is why the model is chosen as the basis for concurrent logic programming. And then the hard part. The stateful models are another story. There is no straightforward way to give a logical meaning to the stateful operation. And the reason, and I think that's a very profound reason, it's because math in general is immutable.
Yeah.
That is the reason. However, stateful models can do logic programming if the state is used in a limited way. For example, it can be encapsulated inside a control abstraction, or it can be used as a parameter to a part of a program. In the first case, we are just enriching the control. In the second case, as long as the state does not change, we can reason as if it were constant. Yeah, in a particular fragment of the program that the state is constant, then it can be seen, it can be used as a constant. But again,
Yeah.
that's very limited power in that case.
Yeah, another approach is to do what Mercury does, which is to do linearity, right? Where,
Yeah,
yeah, basically if you're doing something stateful, the stateful thing can only be referenced in one place, and then you cannot actually observe the fact that it's changing over
yeah,
time.
yeah. That makes perfect sense. The okay, and then the spoilers. Just use constraint-based computation model. It gives techniques for solving complex combinatorial optimization problems. It is the most powerful model in the sense that it's the most sophisticated mechanisms both for specifying and automatically determining the control flow. From the logical programming viewpoint, it has the strongest deduction abilities. This is also missing a portion that it mentions that a particular logical program, I don't remember which one, took 45 seconds to be executed. Maybe it was the Queen's problem.
It's the Queen's problem.
And then it took like half something in the constraint-based one.
No, it's there. It's definitely there. We just kind of skimmed over it because it's the N Queen's problem.
Yeah, and I was like, man, that's I'm very interested to know what type of black magic are they doing there. Where is it? Are you sure?
Uh, oh no, it's the palindromes problem actually. It's
Oh,
the
it's the
very last.
palindromes, right? Yeah, 45
Yeah, right
seconds
there.
and 0.4 for constraint solving. Constraint based. That's pretty impressive. That's pretty impressive, let me tell you. Okay, so let's establish what we're gonna read for next time. We are 11 minutes over, but that's fine. So there we go. We read until, okay, we are here. So going directly to the next one is 8 pages. That's still okay. Going directly to databases is now 13 pages. And going directly to the prologue language, it's 20 pages. Let's do 9, 4, 5, and 6.
4, 5, and 6 sounds fair.
Let me take note. 9, 6. Oh, wait, but then it's gonna be 9, 7 alone.
Um,
Okay, you read
I
all of
mean,
this already. Do you think we can cover all of this in a single shot?
in a single shot, hmm,
9.7 is
maybe.
just introduction to prologue, so I'm not that anxious about it.
Uh, we should be able to. I mean, if we decide to split this, we should probably. But I don't think we need to. I don't think we need to.
Okay, so we're gonna go from 9.4 to 9.7. Finish chapter 9.
Yeah, let's let's be bold. I think it's doable.
Okay, we're gonna do a single session for chapter 10. Yeah, probably because it's like 23 pages, and then we go to chapter 11, which is probably 2 sessions. Yeah, probably true. And then finally, the the spoilers got me excited. I really want to know what type of black magic is going on there.
Um, well,
Okay, actually, this is a good time to ask which chapter is the end, because then we have a single semantics chapter, which is chapter 13. Is this worthwhile reading?
it might be interesting, but whether it's worthwhile to record it is, I'm not sure. I mean, this is definitely interesting from a language design perspective,
So you're gonna read
but
it, and then we have the appendices. I'm gonna stop the recording now.
okay.